The modules 2, 3 and 4 of chapter 7 are devoted to numerical integration. The numerical integration is also known as quadrature. There are three types of numerical integration or quadrature are available in literature. The first one is called Newton-Cotes quadrature formula, second one is called Gaussian quadrature formula, and third one is called Monte Carlo formula. All these formulas are different from each other. In this module, that means in module 2 of chapter 7, we shall consider Newton-Cotes quadrature formula. This formula is obtained by integrating the Lagrange interpolating polynomial for equispace arguments. Now we consider Newton-Cotes quadrature formula. Before going to Newton-Cotes quadrature formula, we define numerical integration and which is defined below. Given a set of points x0, y0, x1, y1 up to xn, yn of the function y equal to fx, this set of points is given. The problem is to find the value of the definite integral x0 to xn fx dx. The function fx is replaced by a suitable interpolating polynomial, that one is denoted by phi x. This phi x may be the Lagrange interpolating polynomial, it may be Newton's forward or backward interpolating polynomial or any kind of interpolating polynomial. Then the approximate value of the definite integral is then evaluated by the following formula. That means integration x0 to xn fx dx is approximately equal to x0 to xn phi x dx. So this is the main principle of the Newton-Cotes quadrature formula. Now we consider Newton-Cotes quadrature formula. There are two types of Newton-Cotes quadrature formulae. One is closed type, other is open type. Now we consider closed type quadrature formula. In this formula, the interval AB, that means the interval of integration AB, is divided into n equispace intervals. That means xi equal to x0 plus ih, where I equal to 1 to n, and the lower limit a is taken as x0 and upper limit xn is taken as b, and h equal to b minus a by n, which is the length of each interval. The Newton-Cotes quadrature formula is considered in the following form. That means integration a to b fx dx is approximately equal to I equal to 0 to n ci yi, where ci are some suitable constant and yr are the value of the function evaluated at x equal to xi. That means equation 2 represents the approximation of integration into a summation. That means integration is replaced by a summation under certain suitable constant c1 to c0 to cn. Now our main problem is to find the values of ci's in terms of xi and yi, where yi is the value of the function f at the point x equal to xi. We know the Lagrange interpolating polynomial phi x equal to summation I equal to 0 to n lix yi, where lix is defined below. In this case, the variable x is replaced by x0 plus sh. That means in terms of equal space arguments, the Lagrangian function Lix is given by minus 1 to the power n minus I divided by factorial I into factorial n minus I, and s into s minus 1 into s minus 2 up to s minus n divided by s minus I. So this is the Lagrangian in terms of new variable s. Then equation 2 is transferred to summation I equal to 0 to n ci yi, which is approximately equal to integration x0 to xn fx dx. And now the fx, the given function fx is replaced by the Lagrangian polynomial. That one is denoted by summation I equal to 0 to n and the corresponding polynomial. And the variable x is given, but the integrand is written in terms of s, and equation 4 is obtained by interchanging the summation and integration. After interchanging summation and integration, we get equation 4, which gives the modified. By comparing both sides, we get ci equal to integration x0 to xn minus 1 to the power n minus I by factorial n minus I into a polynomial of degree n, which is nothing but s into s minus 1 into s minus 2 up to s minus n by s minus I dx. Now we replace the variable x by s, that means gx is equal to h into ds, and the upper and lower limits of the integration are changed to 0 to n. And the terms free from s are taken out from the integration, and the quantity h is replaced by b minus n by h. So this is the coefficient Ci or the constant Ci, which is written in approximate form on the Newton-Cotes quadrature formula, and this Ci is calculated from equation 6 for all I equal to 0 to n, where x equal to x0 plus sh. Then Ci can be written as b minus a into hi, where hi is given by equation 8. The quantities hi's or ci's are called the Cotes coefficient. See that Ci and hi are almost same, only the factor b minus a is multiplied with hi to get Ci. So these constants are called the Cotes coefficient, and these are the very important terms or parameters in Newton's Cotes quadrature formula. Then the quadrature formula 2 becomes integration a to b fx dx approximately equal to b minus a summation I equal to 0 to n hi yi, where all the hi's are calculated from equation 8. So these are the Newton's Cotes quadrature formula without error. The Newton-Cotes quadrature coefficient satisfies some important properties. The first one is summation I equal to 0 to n Ci equal to b minus a, that means sum of all Ci's equal to b minus a, sum of all hi equal to 1. The coefficient Ci are symmetric, that means Ci equal to Cn minus I, that means C0 equal to Cn, C1 equal to Cn minus 1, and so on. Similarly, the other coefficient hi also symmetric, that means hi equal to hn minus I. The Newton-Cotes quadrature formula is derived, and we have seen that this formula depends on the Cotes coefficients Ci or hi, and we have also seen that it is very difficult to find the values of Ci's or hi for general n. So the Newton-Cotes quadrature formula cannot be used to find the integration of an integrable function, but for different values of n we can derive different types of Newton-Cotes quadrature formula. For example, when n equal to 1 we obtain a formula, that formula is known as trapezoidal formula. When n equal to 2 we obtain another quadrature formula called Simpsons one-third formula, and so on. Now we discuss different type of Newton-Cotes quadrature formula for different values of n. When n equal to 1 we obtain a Newton-Cotes quadrature formula known as trapezoidal formula. For this case, the integration a to b fx dx equal to b minus a summation I equal to 0 to 1 hi yi, which is equal to b minus a into h0 y0 plus h1 y1, where h0 h1 are the Cotes coefficient determined from equation 8, and then h0 equal to half and h1 equal to half. After integration we get the values of h0 equal to half and h1 equal to half. Therefore, for n equal to 1 h equal to b minus a, and hence integration a to b fx dx equal to b minus a by 2 into y0 plus y1 equal to h by 2 into y0 plus y1. This is the most simple formula to get the integration or to find the value of integration of any integrable function fx, and the formula is h by 2 into y0 plus y1. This formula can be extended for the whole interval AB by dividing the interval AB into some equal intervals. So this formula is known as composite trapezoidal formula. Here we assume that the interval AB is divided into n equal subinterval as a equal to x0, x1 up to xn equal to b, and the argument are equispaced. Therefore, xi equal to x0 plus ih, where I equal to 1 to n, and h is the length of the subintervals. Then the integration a to b fx dx is equal to x0 to x1 fx dx plus x1 to x2 fx dx plus dot 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 plus xn minus 1 to xn fx dx. And for the first integral, the approximate value of the integration x0 to x1 fx dx is h by 2 into y0 plus y1, and this is the value obtained from trapezoidal formula for the second term. This is the value obtained for the third term, and this value is obtained for the last term. All these values are calculated by trapezoidal formula, and after simplification this formula becomes h by 2 y0 plus 2 into y1 to yn minus 1 plus yn. So, this formula, that means equation 12, is known as composite trapezoidal formula. The error in trapezoidal formula is evaluated by equation 13, E equal to integration a to b fx dx. This is the exact value of the integration minus h by 2 y0 plus y1. This is the approximate value obtained by trapezoidal formula. So, difference between approximate value and exact value gives the error. And to evaluate the error of trapezoidal formula, we assume that there is a function capital F such that capital F prime x equal to fx within the closed interval x0 comma x1. F prime x is the first derivative of f at the point x. Therefore, integration a to b fx dx equal to integration x0 to x1 f prime x dx, which is equal to f x1 minus f x0 obtained by fundamental theory of integral calculus, and after expanding by Taylor series we obtain this infinite series, and after simplification is reduces to h into y0 plus h square by 2 y prime y0 and so on. That means equation 14 gives the exact value in terms of power series expansion of the integration a to b fx dx. Also, by Taylor series expansion we get the value of h by 2 into y0 plus y1, and the approximate value or the Taylor series expansion of this expression is given by equation 15. Now, the difference between equation 14 and 15 gives the error. After simplification we obtain E equal to minus h cube by 12 into second derivative of y at x0 plus dot dot dot, and this can be approximated as minus h cube by 12 second derivative of f at xi, where xi lies between x0 and x1, that means a and b. So, equation 16 gives the error occurred in trapezoidal formula. This is the error in basic trapezoidal formula, not in composite formula. Now, we consider another case of Newton-Cotes quadrature formula. When n equal to 2, the corresponding formula is known as Simpson one-third formula. In this case, the integration a to b fx dx is equal to summation I equal to 0 to 2 hi into yi plus e, where e is the error and hi are the Newton-Cotes coefficients or Cotes coefficient determined by this formula. H0 equal to half into half integration 0 to 2 s minus 1 into s minus 2 ds equal to 1 by 6, and other coefficients are h1 equal to 2 by 3, h2 equal to 1 by 6. In this case, h equal to b minus a by 2, that means the entire interval is divided into two intervals. Therefore, h is equal to b minus a by 2. Then integration a to b fx dx equal to b minus a into h0 y0 plus h1 y1 plus h2 y2 plus the error term, and after substituting the values of h0, h1 and h2 we get the formula h by 3 into y0 plus 4y1 plus y2 plus e, where e is the error occurred in Simpson one-third formula. Note that in this formula the factor 1 by 3 is multiplied with the expression. For this reason, this formula is known as one-third formula or Simpson one-third formula. So, this is the basic Simpson one-third formula, or simply this formula known as Simpson formula. Now, to obtain the composite Simpson one-third formula, again we divide the interval AB into n equal subinterval, but in this case the number of subintervals must be even. So, in this case xi equal to x0 plus ih. Therefore, integration a to b fx dx equal to integration x0 to x2 fx dx plus integration x2 to x4 fx dx and so on. Lastly, integration xn minus 2 to xn fx dx. That means the entire integration is decomposed into n by 2 sub problems. And the value obtained for the first integral is h by 3 y0 plus 4 y1 plus y2 obtained by Simpson one-third formula, and the value for the second integral is this one, and value for the last integral is this one. After simplification, the formula becomes h by 3 into y0 plus 4 into y1 plus y3 plus dot 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 plus yn minus 1. That means 4 into sum of the y's with odd suffixes plus 2 into sum of the y's with even suffixes plus yn. So, this is the composite Simpson one-third formula. The expression for error in Simpson one-third formula is calculated below. Ex equal to difference between the exact value of the integration and the approximate value obtained by Simpson one-third formula. After simplification, that means after expansion by Taylor series, we obtain the error Ex equal to minus h to the power 5 by 90 fourth derivative of f at xi. That means equation 23 gives the error in basic Simpson one-third formula, where xi lies between x0 and x2. And for composite Simpson one-third formula, the expression of error is given by equation number 24. Now, geometrically the Simpson one-third formula looks like this. In this formula, that means in Simpson one-third formula, the given function y equal to fx is replaced by a parabolic curve ABC. That means the area obtained by the Simpson one-third formula, that means the area of the curve ABC DE. The area bounded by this region is nothing but the value of the Simpson one-third formula. That means the integration, the entire integration is approximated by the area enclosed by the points A, B, C, D and E. Now, we consider one example to illustrate the trapezoidal formula and Simpson one-third formula. Here we consider the integral is integration 1 to 3 x plus 1 e to the power x square dx. In this case, we shall calculate the value of this integral by Simpson one-third formula as well as by trapezoidal formula by taking 10 intervals. That means, in this case n is 10, lower limit a equal to 1, upper limit b equal to 3, and the function fx equal to x plus 1 into e to the power x square. Therefore, h, the length of the interval is 3 minus 1 by 10, which is equal to 0.2, and this is the tabulated value of x and y obtained from the function. And by trapezoidal formula, the expression is this one, and after simplification we get the value of the entire integration, which is equal to 6149.2217, and by Simpson one-third formula, the formula is this one, and after simplification it becomes 5557.9445. So, note that these two values are different. It is generally happens because the Simpson one-third formula gives more better result than the trapezoidal formula. Now, we consider the case when n equal to 3, and the formula obtained by this value is known as Simpson 3/8 formula. In this case, the integration x0 to x3 fx dx is equal to summation I equal to 0 to 3 ci yi plus e, which is equal to b minus a into summation I equal to 0 to 3 hi yi plus e is the error, and the Cotes coefficients h0 equal to 1 by 8, h1 equal to 3 by 8, h2 equal to 3 by 8, h3 equal to 1 by 8. All these values are determined from equation 8, which is the expression for h. In this case, the length of the interval h equal to b minus a by 3. Thus, integration a to b fx dx is equal to this expression. After substituting the values of h0, h1, h2, h3, this expression reduces to this expression, and finally it becomes 3h by 8 into y0 plus 3y1 plus 3y2 plus y3 plus error term. Note that here the factor 3 by 8 is multiplied by the entire expression. So, for this factor 3 by 8, the formula is known as Simpsons 3/8 formula, and the error of this formula is given by minus 3 by 8t h to the power 5 into 4th derivative of f at xi, where xi lies between x0 and x3. Obviously, this formula is known as Simpsons 3/8 formula. Now, you consider the case n equal to 4. In this case, the integration a to b fx dx is approximated as x0 to x4 fx dx, which is equal to b minus a into summation I equal to 0 to 4 hi yi plus e, where the Cotes coefficients h0 equal to 7 by 90, h1 equal to 32 by 90, h2 equal to 12 by 90, h3 equal to 32 by 90, and h4 equal to 7 by 90. So, using these values, the formula is finally reduces to this one obtained by equation number 29, 2h by 45, 7y0 plus 32y1 plus 12y2 plus 32y3 plus 7y4 plus e. And the error term of this formula is minus 8 into h to the power 7 by 945 into 6 derivative of f at xi, where xi lies between a and b. This formula is known as Boole's quadrature formula. Now, in case of n equal to 6, we obtain another formula known as Vaders Formula, and this formula is given by this expression, where h0 to h6 are the 7 Newton Cotes coefficients, and these values are given by equation 30. Using these values of h, we obtain the Vaders rule as integration a to b fx dx equal to 3h by 10 into y0 plus 5y1 plus y2 plus 6y3 plus y4 plus 5y5 plus 6y6 plus e is the error term, and this formula is known as Vaders formula for n equal to 6. So, we have derived 5 quadrature formula or 5 particular cases of Newton Cotes quadrature formula, and we now discuss the degree of precision of quadrature formula. This is very important to distinguish between the best quadrature formula with other quadrature formula. For trapezoidal formula, the degree of precision is 1, means the trapezoidal formula gives exact result when the polynomial is of degree 1. The degree of precision of Simpson 1/3 formula is 3, that means the Simpson 1/3 formula gives exact result if the polynomial is of degree 3 or degree less than 3. The degree of precision of Simpson 3/8 formula is 3, which is equal to the degree of precision of Simpson 1/3 formula. Degree of precision of Boole's formula is 5, this is higher than Simpson 1/3 formula, and degree of precision of Vaders formula is 5. That means Vaders formula and Boole's formula gives the correct answer if the integrand is a polynomial of degree up to 5. So, this table shows that the Boole's and Vaders rule gives more better result than the other formulas, that means trapezoidal rule, Simpson 1/3 rule and Simpson 3/8 rules. So, all these formula are applied to find the integration of any kind of integrable function, but if the integral is improper, first type or second type, then the previous formulas cannot be applied to find the integration of such type of integrals. Now, we consider another type of Newton Cotes quadrature formula called OpenType quadrature formula. So, in Newton Cotes closed type formula can be applied for second type improper integrals by choosing appropriate arguments, but it is not always possible. But this formula can never be used for first type improper integral, because in first type improper integral the limits are infinity, minus infinity or plus infinity, therefore the length of the interval h is also infinity. And if the integrand fx has infinite discontinuity at the end points of the interval, then also the closed type Newton Cotes quadrature formula cannot be applied. So, for this case, a new kind of Newton Cotes quadrature formula are derived, and this type of formula is known as OpenType Newton-Cotes quadrature formulas. The first one is called the midpoint formula. This is a very simple formula, and the formula is integration x0 to x1 fx dx equal to h into f of x0 plus h by 2, where x0 plus h by 2 is the middle point of the endpoints x0 and x1, and the error term is 1 by 24 h cube into second derivative of f at xi lies between x0 and x1. This is the very simple formula to calculate the integration of a function fx excluding the points x0 and x1. Now we consider another formula known as 2-point formula. Here also the integration x0 to x3 fx dx is equal to 3h by 2 f of x1 plus f of x2. In this formula also the endpoints x0 and x3 are excluded, and the red terms indicates the error term. The 3-point formula is this one, x0 to x4 fx dx equal to 4h by 3 into 2 f of x1 minus f of x2 plus 2 into f of x3 plus error term, and that one is 14h to the power 5 by 45 into 4th derivative of f at xi. That means this formula gives the correct answer for the polynomials whose degree up to 3. So in this formula also the argument x0 and x4 are not included in the formula. That is why this formula is also known as the OpenType formula. And this is the 4-point formula, 4-point open formula, and this formula is also applicable, or this formula gives the exact result for the integrand fx, which is a polynomial of degree up to 3. Because the error terms involve the 4 derivatives, that means this formula gives correct answer for the polynomials of degree up to 3. So these are the 4 Newton-Cotes quadrature formula, and these formulas are called the OpenType formula. In this module, general Newton-Cotes quadrature formula is derived, and for particular values of n, that means for n equal to 1, 2, 3, 4, we derive different Newton-Cotes quadrature formula known as Trapezoidal formula, Simpsons 1/3 formula, Simpsons 3/8 formula, Bool's formula, Vaders Formula, and many others. All these formulas are applicable for proper integral, but if the integral is improper, first type or second type, then this formula cannot be applicable. For these problems, one can use the Newton-Cotes OpenType formula. That means the Newton-Cotes OpenType formula can be applicable for second type improper integral, but also these formulas are not applicable for first type improper integrals.